In this video, we'll be learning all about piecewise-defined functions. We'll learn about what they are, how to compute their outputs, how to graph them, and how to find their domain and range. A piecewise-defined function is a function that has different formulas for computing the outputs for different inputs. Let's take a look at an example to get an idea of what they are. In this example, we have a function named f, and when we input x into our function, we have different formulas to compute the output depending on what our x value is. This function tells us that if our input x is between -3 and 0, then we would use x squared to compute the output. If our input x is equal to 0, then our output is 2. And if our input x is greater than 0, then we would use the formula -2x plus 5 to compute the output. The pieces of a piecewise-defined function are these different groupings of x values. We would say that the first piece of this piecewise-defined function are these inputs that are between -3 and 0. The second piece of this piecewise-defined function is when the input is equal to 0. And the third piece of this piecewise-defined function are the inputs greater than 0. So now that our function is defined, let's get some practice evaluating outputs. Let's start by evaluating f of -2, meaning let's find the output of this function when the input is -2. First, we need to decide, is the input -2 part of the first piece, second piece, or the third piece? Because that will tell me what formula to use to compute the output. Well, -2 is in the first piece because it's a number that's between -3 and 0. And so to compute the output, we would use the x squared formula. So f of -2 would be -2 squared, which gives us +4. Next, we want to evaluate f of -1. So what's the output of this function when I input -1? Again, decide which piece -1 is in. And once again, -1 is in this first piece because it's a number that's between -3 and 0. And so to compute the output, we would use the x squared formula. So f of -1 would be -1 squared, which gives us +1. Next up, we have f of 0, which means we want to find the output of our function when the input is 0. The input 0 falls in this second piece, which means that if we want to get the output, we would use the second formula. Since the formula is just 2, f of 0 is 2. Next, we have f of 1. So we want to find the output of my function when the input is 1. So let's determine which piece it's in. The input 1 is in the third piece because it's an x value that's greater than 0. So to compute the output, we would use the third formula, -2x plus 5. So f of 1 would be -2 times 1 plus 5, which gives us 3. Lastly, we have f of 2. So we want to find the output when the input is 2. Again, let's decide which piece it's in. Is it in the first, second, or third piece? Well, 2 is a number that's greater than 0, so it's in the third piece, which means that we would use -2x plus 5 to compute its output. So f of 2 would be -2 times 2 plus 5, which gives us +1. Now that we know how to find the outputs, let's try to graph this function. To graph a piecewise-defined function, the first thing we'll do is we'll take our xy plane and separate out the different pieces. So we'll draw vertical dotted lines to separate the different pieces. Our first piece starts at x equals -3 and goes up to x equals 0. So we're going to start by drawing a vertical dotted line at -3 to indicate where our first piece begins, and we'll draw a vertical dotted line at x equals 0 to indicate where our first piece ends. Our second piece is x equals 0, which we already have a dotted line for, so we don't need to draw anything else. And our third piece is x greater than 0. Again, we already have a dotted line at x equals 0, indicating where our third piece begins. And since our third piece doesn't have an ending x value, it just goes on forever to the right. Now that we've separated the pieces, I know that on this first portion of x values from -3 to 0, my function is going to behave like the x squared function, which means that I would be graphing y equals x squared on that portion of x values. At x equals 0, my second piece, I know that the output is 2, so essentially I just have to point 0, 2 there. And then lastly, for x values greater than 0 on this right-hand side, my function is going to behave like -2x plus 5. So on this portion, we're graphing y equals -2x plus 5. So let's start by graphing our first piece using the y equals x squared formula. Now, if you don't know what the shape of this function is, we can always make a table of values. When I'm making my table of values, I want to include all of the x values that are in our first piece, including the boundaries. So I'm going to start at -3, then -2, -1, and then going all the way up to 0. So we're working with y equals x squared. At -3, the corresponding y value would be -3 squared, or 9. At -2, we've actually computed the output there already. We got that was 4. At -1, again, we computed the output earlier. We got that the output is 1. Lastly, at x equals 0, plugging that into x squared, 0 squared gives me 0. So now let's plot our points. We have -3, 9, which is up here. -2, 4 is over here. -1, 1 is over here. And then 0, 0. Connecting our points together, we see that our graph looks roughly like this. Now, to finish off this first piece, we need to look at the boundaries to decide whether the point is actually included or not. So let's look at this left boundary at x equals -3. We want to ask ourselves, at -3, is the point -3, 9 actually on our graph? So looking at our first piece, we see that -3 is part of this first piece. So this point here is part of my graph. So I'm going to fill this in with a solid point. Let's now look at the right boundary. The right boundary here at x equals 0, we want to ask, is this included in our first piece? Well, looking at the inequality symbol here, 0 is not part of the first piece, so I wouldn't actually have the point 0, 0 here, which means that I should replace this point with an open circle. So this completes the first piece of our graph. The second piece of our graph is just at x equals 0. Again, the output at x equals 0 is 2, so we just have the point 0, 2 on our graph. And that's all we have to do for this second piece. For the third piece of the graph, we're looking at x values greater than 0, and we're graphing y equals -2x plus 5. Again, if we don't know what the shape of this graph is, we can always make a table of values. When I select the x values on this piece, I always want to make sure to include the x value on the boundary. So we're going to start at 0 and then do 1, 2, and maybe 3. So now let's use the formula y equals -2x plus 5 to help us compute the y values. If we plug in x equals 0, -2 times 0 plus 5 gives us 5. If we plug in 1, we've already computed this earlier, -2 times 1 plus 5 gives us 3. If we plug in 2, we have -2 times 2 plus 5, that gives me 1. And then lastly, if I plug in 3, -2 times 3 plus 5 gives us -1. Let's now plot these points that we've found. We have 0, 5, we have 1, 3, 2, 1, and then 3, -1. We can then connect our points together with a straight line. One last thing to do is go to our boundary at x equals 0 and decide whether or not we actually have this point 0, 5 on our graph. And it depends on our inequality symbol here. Here, our third piece is x values greater than 0, so we don't actually want to include the point at x equals 0. So I'm going to replace this point 0, 5 here with an open circle. So this completes the graph for our piecewise defined function. So essentially what we did was we graphed the x squared function for x values between -3 and 0. At x equals 0, we graphed the point with y value 2. And then for x values greater than 0, we graphed -2x plus 5 to get this line. Now, to decide whether boundary points are included or excluded, we basically look at the inequality symbols of these pieces. If there's an equals to on the inequality symbol, we include the endpoint. If there is no equals to on the inequality symbol, we exclude the endpoint and leave it as an open circle. Now, one last thing that we want to do is to find the domain and range for this function. Remember that the domain of a function are the valid inputs to your function. Now, there are certain x values that we can't plug in. For example, we can't plug in x equals -4 because -4 is not in any of our three pieces. So there isn't a formula that we can use to get the corresponding output. Essentially, for piecewise defined functions, the domain consists of the x values that are in each of your pieces. Those are the x values for which you have instructions for how to compute the output. So to find the domain, typically what I'll do is I'll draw a number line and illustrate on the number line the x values in each of our three pieces. In our first piece, we have the x values from -3 to 0, including -3, but excluding 0. So we have this region on our number line. In our second piece, we have instructions for x equals 0. So I'm going to fill in x equals 0 on our number line. Our third piece tells us that we have instructions for what to do if x is greater than 0. So on our number line, let's highlight the region of x values greater than 0. So now looking at what x values we have on this number line, we see that our domain is the interval -3 to infinity. As for the range of this function, we need to look at the graph. Remember that the range of a function corresponds with the outputs, or the y values that you have in your graph. So looking at our graph, we want to ask ourselves, do we have a lowest point on our graph? And do we have a highest point on our graph? When we trace our graph to the right, we see that the graph keeps on going down forever. So there's no lowest point on our graph, which means that the lower bound here is going to be -infinity. When we trace our graph to the left, we see that our graph stops at the point -3,9, and this ends up being the highest point on our graph. So the upper bound for our range is going to be 9. And since we have points with all of the y values in between, our range for this function is -infinity to 9. So in this video, we learned what a piecewise defined function is, how to evaluate them, how to graph them, and how to find their domain and range. In our next video, we'll look at more examples of piecewise defined functions.